So hello everyone, my name is Lalit and I work on database for a very long time now and recently started working on the PostgreSQL. The today topic is about learning one of the component of database which is very common across all database systems, that is the memory part. And in a PostgreSQL, while learning the PostgreSQL and while reading about the PostgreSQL internals, this is something I found about the PostgreSQL buffer, shared buffer, and know how it works, how it fetch data from disk to memory to speed up our database operations. So the topic is about knowing the components of buffer manager. So far we only know when we talk about the memory, we talk about the different buffers of PostgreSQL. That includes maintenance buffer, shared buffer, the major memory components. But in along with the shared buffer, there is a internal structure which manage how pages are loaded from the data, from disk to memory, and how data are flushed from memory to disk, okay, vice versa. And that is something we are going to discuss today as a learning part, okay. With some some concept like how page is cached and how pages flush, dirty pages are flushed from memory to disk. So I'll start why buffer is important. Again, just to give a summary, just to speed up our data operation. That is the core objective of having a memory in any database. Okay, it acts as a gateway. So if you are performing any operation, it goes to the memory operations. The primary objective is fast travel of data, which ultimately achieves the good operations, good IOPS. Okay, that's resulting in good IO efficiency. So this is something why we need a buffer and memory in the database. Okay, so we'll talk about the structure of buffer in the PostgreSQL. Generally, as I mentioned, when we talk about the buffer, we also only talk about the shared buffer. Okay, but there are more components in it, and know how page load and know how pages identify by the memory. Okay, how data is requested, how particular page is identified in the memory, how it is stored, how the mapping is stored. That kind of internals we are going to learn in this talk. So we'll start with the first layer, that is the buffer table, okay, which keeps the information about the buffer tag. Buffer tag consists of table space ID, my DBO ID, my table ID, and the fork number and the block. Fork number is nothing but whether it's a free map space file or a visibility file or the data file. So you can see this is kind of an identifier for a memory to locate the particular object or the data you are looking for. That's the first layer. It is basically the hash table, okay, what we have in the first layer. And in the second layer, we have buffer descriptor, which keeps the information about particular page slot is metadata, whether it's dirty or not. Dirty in the sense if it is in use, who will be the next page to load in the memory, who will be the next page which we need to evict from the memory. So that kind of a pointer and that kind of information will be kept under the buffer descriptor. It also keeps the buffer ID, which I am going to explain in the next layer. But these are the things. I will also explain the state of the buffer descriptor in the later slide. But for now, you can understand the buffer descriptor will keep the metadata, the tag ID and buffer ID, all information about the page, okay, which is in the memory. In third layer, we have the buffer pool. Buffer pool is an array of buffer IDs. Basically, it's a 8 KB page. So one page can contain, one slot can keep whole page. Okay. So this is the basic structure of the buffer manager, in our PostgreSQL memory. So we'll move on to the so the question comes when your PostgreSQL starts, how it looks like, right? Because what we saw that when the database is running, that time we have the pages and all those things. But when your database starts, this is how it look like. Okay, there is a free list, there is a empty descriptors, buffer descriptors, empty slots load into the memory, whatever memory you assign to your shared buffer, that load get loads, and immediately after that the first page mark as pinned, and it gets the buffer tag and buffer ID, and that's how the memory operation starts in the buffer manager. So just to give example, this is how the flow works. Backend process request for the particular page, and it generates in our layer 1, it generates the buffer tag, okay, to identify the particular object you are looking for. The buffer table has a mapping of your buffer tag and buffer ID. So it has all information to access your page from memory, or if that page is not exist in the memory, it will go to the disk. Okay, that we'll see later, but buffer table work is to have the mapping of your buffer tag and buffer ID. The buffer descriptor will have the metadata of buffer ID. It is not a metadata about the actual data, okay, the database or the table data. This is the metadata that what is the buffer ID and what is the buffer tag. Okay, so that information kept in the buffer descriptor, and with this information finally it goes to buffer pool and get my page, which we called as a buffer slot. Okay, so that's how if you want to visualize, that's how the flow works generally. This is just for a reference, I added in a slide, so later people can read it. So yeah, there are two scenarios, whether it can be a hit or miss. Okay, my data can be in the shared memory, or it can be on the disk. So first my query comes looking for a particular page, and if that page is not available, that mapping is not available in buffer table, it goes to disk, fetch that data, but along with the fetching that data, it also buffer that data for the next retrieval. So that's one case, and the second case is cache hit. When the cache is hit, what I explained in the earlier slide, it goes to the buffer table, buffer descriptor, and pull the page, or the page in the buffer pool it called as a slot. Okay, so that's how flow works. Okay, so here there are few important things that how my buffer knows which page to keep and which page to flush. Okay, that is something we are going to discuss in the next slides. So basically, again, this is a theoretical description of that diagram which I explained. Now we'll talk about the concurrency. Okay, since our backend processes, we have a multiple backend processes accessing same hash table or same page slot, it is possible that there could be a corruption, memory corruption or a conflict, and to manage that, shared manager has some lock-in mechanism, which is it has a buffer mapping log to keep the consistent data in my buffer table. Okay, and content log, for example, there are two or more than two processes trying to access same page data, okay, insert or update. In that case, it will take exclusive log on that, and if it is trying to read, it will have the shared log. So this is how the even in a memory, this is how locking will take care. Locking makes sure that there is no memory corruption, and everything, my data mapping is correctly mapped and consistent with multiple backend connections. Okay, so this is how locks are managed. Now coming to the how once I have buffer loaded and everything is there, I need to keep recycling the data to add recently used have recently used data in the memory and flush the unused data from the memory. Okay, to do that, PostgreSQL use clock sweep algorithm, which works on this factors. So there will be So the page will or the particular slot will mark as pinned, unpinned and the empty state. These are the 3 states we have, and there is one more state called dirty state. That's why you called as a dirty pages, right? So obviously the page is pinned means that page is currently in use and the currently in use. So it will be not the candidate for my not the candidate for victim, next victim. Then there is a concept of unpinned buffer. So there are 2 factors inside that. Okay, how this pin, unpin and empty is decided. So there are 2 variables, 2 counters I would say. There is one is reference count and the second is usage count. The reference count is when page is getting accessed, the reference count is 1, and whenever that page in use there will be the reference count is 1. The moment it's not in use, the reference count will go back to 0. Okay, that's the one counter. So the value will be 1 or 0. So that's how we identify whether my page or slot is pinned or not, okay, in the memory. And then unpinned buffer, that page or slot in the memory, but it isn't used by the it is used by the backend processes. Okay, so let's say there are 2 backend processes which use this slot. So I'll keep it for now. And let's say third is unpinned one, that means it is not in the use, plus the usage count is 0, or let's say one page has usage count 3 and the other page has usage count 1. So the page with the lower count usage will be evacuated immediately as a dirty page, okay, because very less number of processes use that. So depending on these 3 factors, the page will be evicted from my memory, okay, and the slot will be available for new data, okay. So to do this all job of evicting and flushing the dirty page, there are 2 processes: background writer, which works as per need, okay, as needed, okay, and there is a frequently run task as a check, the background process as a checkpointer which do this task frequently. So there are 2 background processes which are helping buffer to make sure that the data is reused, okay. So most of the database use list entry, list latest or list use, list recently used, that kind of thing. But it's similar to that. The clock sweep is similar to that, okay. That algorithm used here. So this thing. Okay, so what happened when you have a large number of sequential read? There is a chance that because of a single read, my whole the shared buffer pool will get evicted and all pages will flush to disk. So to avoid that, there is a concept of ring buffer which makes sure that such reads will not affect the shared buffer, okay, and will keep the most used or frequently used data in the shared buffer. And for example, the second is the local buffer which used for the temporary table. So these kind of a buffer will make sure that the shared buffer data which is used frequently will not get flushed because of such kind of operations. So in a summary, what we discuss, in a memory it's not just a shared buffer, it has the components. It is shared buffer pool, hash table and descriptor which keeps the data about the our page, metadata about our page, and that's how the memory knows which data to keep, which slot to keep, how to give the access to a particular backend process, how to evict the data from our memory. Okay, so these are the components I use. To maintain the concurrency, there are lightweight locks which keep the consistent data and reduce the chance of memory corruption, okay, while handling the multiple background connections. We talk about the algorithm and how cache hit and cache miss works. Optimization, just to know, for optimization there is a ring buffer and a local buffer, okay, to make sure that some few kind of operation will not affect my shared buffer data. And for durability, we have the helper background processes which keep the buffer clean, and it keeps the space for most recently used data. So that's all about it. You will get the slides here, and as I mentioned, if anyone want to learn about the PostgreSQL internals, I think this is one of the best, I would say so far best reference I found. Mr. Suzuki wrote this ebook, it is freely available. So this internal topic I selected from that book only, and along with that there are multiple topics, okay, and anyone wanted to learn about the PostgreSQL internals, how it works on a code level, okay. So this is a very good reference I can suggest, okay. So please take a look, and yeah, just scan the barcode and there you will get these slides. Thank you.